All right. So before we start, are there any questions concerning the last lectures? I will assume not and share my screen. Okay, you're likely seeing a black screen now. Yeah, so this last lecture will concern my job. So what exactly I did during my master's degree. We will review a little bit about the previous lectures and then introduce some new concepts to understand what is the functional renormalization group, which is the main tool I applied to QFTCS during my master's. And of course, feel free to interrupt me whenever you wish. So, as we said before, I like to start talking about quantum field theory by thinking about silly questions, such as how did the universe begin, what is time, what are things made of, can we go back in time, and why do things fall? Mainly, we focus on why do things fall and what are things made of. I talked to you about how the Greeks already had answers to this in the forms of five elements and their natural motion, while nowadays we answer these things in terms of the standard model and general relativity. Five elements in natural motion are in agreement with each other, while the standard model and general relativity appears to be in conflict in the sense that they work with different structures. General relativity is briefly the statement that spacetime tells matter how to move, while matter tells spacetime how to curve. And we improved on this by going to quantum field theory and curved spacetime, which, in addition to this relation between classical spacetime and classical matter, we also allow spacetime to tell quantum fields how to move. Some of the applications were the Hawking effect, in which we perceive black holes as being hot, with a temperature inversely proportional to their mass, in the case of a Schwarzschild black hole, and the Unruh effect, in which an inertial observer may see spacetime as being empty with no particles and at 0 Kelvin, while an accelerated observer sees the same spacetime in the same conditions as being with a temperature proportional to their acceleration. Now, another application that is interesting on this concerns particle detectors. So we can give a particle detector to two different observers, and, for example, entanglement between the particle detectors might allow them to communicate. However, a more interesting thing to do in quantum spacetime, in curved spacetime, is to allow these particle detectors to interact with a quantum field, and by means of the quantum field, allow communication with each other. This is what my advisor discussed in 2016 in a paper in which he allowed the particle detectors to interact with the field, and that's in a more general way than we considered last class. But he considered that there was no energy gap between them. So let me just. So the detector Hamiltonian was in fact not omega 2 over 2, omega over 2 sigma z, but rather it was simply zero. This model has a few advantages. For example, it can be solved exactly, which is rare for a quantum theory. It is valid in many spacetimes. There is no need for for a notion of particles, so we do not need to choose a representation of the algebra of the field. The observers can be in arbitrary motions and they not need to be inertial or uh, accelerated at a constant rate. Interactions happen only in a bounded regions of spacetime, which is just as happens in reality. We do not interact eternally, and we do not interact on an unbounded space-like region. We interact only on Earth. This is valid in many states, namely in any Gaussian state. It allows classical communications, and it is manifestly causal. However, it is difficult to perform quantum communications because you need extra entanglement between the parts, and they cannot be used as particle detectors since they have no gap. A way to improve on these two issues is to allow the same interaction, but allow for a non-vanishing gap. So we are going to work with, sorry, let me just,
So maybe naive question, but by no gap, do you mean that there's only one level, or there are many levels continuously separated? Or
sorry, I did not
am I
understand your
audible?
question.
I mean, by no energy gap, do you mean that there are many continuously separated levels, or there is only one state? You're taking Hamiltonian to be zero.
Yes, I'm picking in here, I am picking the detector Hilbert space to be C2,
Mhm.
but I'm putting no energy gap, so the Hamiltonian is zero in the sense that both the down state and the up state have the same energy, zero.
Okay.
Okay?
Mhm. So up and down states have same energy. Does it mean that they are basically same?
Yes, they're basically the same. They're different states, but they have the same energy.
Okay. Okay.
You're welcome. So a way to improve on these difficult quantum communications and on the absence of particle detectors is to consider the same interaction but allow now for a non-vanishing gap, so that now the Hamiltonian is just as we had last class, in which it is omega over 2 sigma z. So we now have a difference of energy between the up and down states. Now this allows for simple quantum communications. The qubits can be used as particle detectors, but it has no exact solution, which means that we no longer can assume that the interaction is arbitrarily large. To keep an arbitrarily large interaction, we would like to do perturbation theory in the energy gap rather than in the interaction, and perform a renormalization group improvement to keep non-perturbative results. So this led me to study non-perturbative aspects of quantum field theory in curved spacetime, which was my master's at the Federal University of ABC, funded by both CAPES and FAPESP, which are scientific financing institutions in Brazil. Now, the renormalization group is a manner of considering how different scales relate to each other. For example, when we try to study water, we can start with atoms, uh, how atoms work, then atoms form molecules, molecules can form droplets of water, these droplets can form oceans, for example, or big bodies of water, and eventually oceans in the whole earth. Now, the randomization group tells us how to go from one of these to the other by zooming out on the theory. So in principle, everything about water is containing the information about the molecules, but we can zoom out and disregard some of the details of the molecule approach to keep only effective theories about how a droplet works, about a huge body of water works, or about how the oceans work. So we just keep zooming out and losing a bit of information. And in this way, we can understand better a theory at the determinate scale we are interested in. The renormalization group is a way of doing this for quantum field theories. Now, another example is, for example, in the standard model, where we have the decay of the muon as being described by the muon comes here, it decays into a neutrino and a W boson, into a muon neutrino and a W boson, and later the W boson decays into an anti-electron neutrino and an electron. Now, another way of seeing this, if you're not interested in the details of the decay, is the so-called Fermi interaction, in which we just have the muon decaying directly into a muon neutrino, an anti-electron neutrino, and an electron, and the W boson is considered for in this interaction and how exactly the interaction happens. So this is a way of zooming out a quantum field theory. Now we have many ways of interpreting how we want to do. And first, we can consider all modes of a theory, and this will give us what we call the effective action or the quantum action, which has all quantum effects considered. We can consider no quantum effects, in which case we have only the classical action with no quantum effects at all. Or we can do a compromise between both ideas and try to consider only quantum effects from the ultraviolet until some stopping point in the middle, which will give us what we call the effective average action. It has some quantum effects only from a scale k upwards, and hence it is adequate. It has considered all of the effects from the scale k upwards, and is therefore an effective description at the scale k for what exactly is going on. Now, to actually consider this way of integrating only a piece of the modes, to considering only part of the modes, we actually need to have some sort of cutoff that is going to give us what is the region we're interested in. Typically, we use a function of this form, which will suppress lower energy modes, while it will leave high energy modes free to be considered in the path integral formulas eventually. Now, we also need to consider a truncation to make the infinitely difficult problem of considering how exactly that action is going to be. So instead of solving exactly for an action, for that quantum effect, for the effective average action, we're going to consider only some interactions that we're particularly interested in and make a truncation. And ideally, this truncation in yellow is going to be this truncation in here is going to be similar to what we would get if we consider the exact truncation and then projected it onto the space of parameters you are interested in. So first we need to consider what is a good ansatz for the problem that we want to solve that considers that those particle detectors interacting with a quantum field. What we consider is the following. We have these two energy levels, and in order to actually quantize them, we have two ladder operators that can be quantized by using Grassmann variables, which are anti-commuting variables, but this cannot deal with the field coupling. So instead, we follow the paper by Burbano, Perge, and Torres, which introduce a true vacuum between these two up and lower states. This is similar, for example, how in an atom you have different energy levels, and you can consider that an electron directly jumps from one level to the other, or alternatively, what you have is that you have an electron in one level, then you go to the vacuum of quantum electrodynamics, then the electron is created elsewhere. This is similar to what is happening here. So we introduce a true vacuum where the detector is at no up or down, but it's rather at a non-excited state, at a true vacuum state, and we then can quantize these four ladder operators. This gives us an effective average action that has the quantum field and all its corrections, plus interactions on the quantum field, and many other interactions that we can consider. We have the possibility of incoming up an up state going to the vacuum and then come in an up state again, which is what determines the energy gap for the up state. The same thing for the down state. And then we have the possibility of the up state becoming a down state through the interaction with a photon, with the quantum field, and the same thing from the down state to the up state. So this here is the field description. This here corresponds to HD, which is a free Hamiltonian for the detector, and this here corresponds to the field detector interaction. Now, in addition, we need an ansatz for RK, which is our cutoff. So what we decided to use was to consider RK as being an extra gap term in the detector. Usually, people use an extra mass term, but since the detector does not have a mass, but it has a gap, we decided to use an extra gap. Using these ansatz for the effective average action and for the ansatz and for the cutoff RK, we can find the RG flow by using functional traces. However, these functional traces are difficult to compute. They typically have the form of the trace. I'm actually going to skip this part because it is a little bit technical. And we found, after computing the traces, that some integrals diverged. For example, the beta function, which is what rules the renormalization flow for one of the couplings, had this behavior in which the smaller the gap, the larger the beta function, and it is divergent polynomially, as you can see in here. So it has a behavior of 1 over x. I think it is 1 over x. It might be 1 over x to the n. And hence this leads to a problem because the RG flow is not well defined. We found that the integrand, while this might seem like an infrared problem, we found that the integrand is actually larger and larger at the UV scales, and hence it seems like a problem at the UV. Here's the plot of the integrand in terms of the energy scale on many different gap values. So you might have a problem with the way we computed the traces, in particular the convergence radius of the series that occurs when we are computing the traces, which leads to some issues. However, after performing a Fourier analysis calculation of the same thing, we obtained good results and the same results as the trick that I used to make the calculations. Then we have the issue of choice of cutoff, and we decided to compute one loop results to see what happens. And the one loop results actually walk. So it seems that the choice of cutoff might be wrong, and it might be interesting to choose a different cutoff ansatz. At last, there are formal manipulations everywhere during the calculations that might be an issue, and that should be needed to be diagonalized in the functional matrices to actually be well defined. But the one loop results suffer of the same issues with formal manipulations, and they still work. Hence, the main problem seems to be the choice of cutoff, and indeed, since this presentation was done, we did a different choice of cutoff by altering that decaying scheme into a growing scheme, which is difficult to interpret, but it seems that it worked and it gave us finite results compatible with MS bar, which is what we used for the one loop result. Hence, the history begins with Aristotle with five elements in natural motion. Eventually, Einstein finds out about general relativity. Fermi finds the weak interactions that I described while discussing the renormalization group. Many physicists developed the standard model. Hawking found out about the Hawking effect between 74 and 75. Unruh found out about the Unruh effect in 76. Many physicists developed the functional renormalization group from 93 to 94. My advisor on DUFU prescribed his non-perturbative communication protocol in 2016. Bourbon Pachentot has prescribed their way of describing a path integral for a particle detector in 2021. And in 2021, I started my project on non-perturbative aspects of quantum field theory and curved spacetime and found an ansatz for the effective average action. Found eventually an ansatz for the cutoff, while in principle wrong, eventually got it right. Developed a way of calculating the difficult traces that occur in the middle of the calculation. Found gapless divergence in the FRG flow, which would later be fixed. Saw that Fourier analysis and the Taylor trick lead to the same results. Performed a one-loop analysis which matches the non-perturbative calculation, and filled in my dissertation some pedagogical gaps in the literature. So what lies ahead to this project is to try new cutoffs, which we actually did and found cutoffs that work. Try to include more detectors to see how exactly they may interfere with each other's renormalization flows. Study more of these compact interactions, which are interactions in a restricted region of spacetime, which are hardly ever considered in quantum field theory. Usually considered interactions that happens everywhere. Try to develop these calculations for higher spins, and eventually try to apply some of these ideas to quantum gravity itself. In any way, it is interesting to see how these ideas have been blossoming, and it is curious to think about what lies ahead in the future.
Yeah, sorry, but could you just interpret how do you put that cutoff?
Sorry?
I mean, could you just elaborate how do you put cutoff? You just arbitrarily put
How do you use the cutoff in the functional normalization group?
yeah.
Okay, let me share a different screen now. How do I stop share? What happens in the functional normalization group is that usually you define a generating function in quantum field theory through a path integral in this way. So there's e to the is to the is. Yeah, I'm going to use an Euclidean signature, which is minus s. It has the field in here, and plus j times the field integrated over the field. The way you use the cutoff is you input an extra term in here, which is going to be a delta sk phi plus j phi field, where this delta sk of phi is given by half the field, the cutoff, which depends here on momentum, so minus del 2 phi delta x. So we introduce this term, which is quadratic in the field, so it resembles a mass term. And what happens here is, let's pretend this is a mass term. So pretend that this is actually k squared phi 2 d4x squared. Then you have an extra mass term in here, and this mass term means that energies lower than this mass scale are not going to be excited because you don't have enough energy to create a mode. However, for higher scales, you can excite these scales without any problems. So introducing this cutoff in here allows you to pick the path integral and restrict it to only the scales you're interested in integrating out.
So, we are in curved space, right? So we can
Sorry?
do it in different. So we are doing this in curved space. So we can do it in an observer independent way. I mean, this cutoff doesn't depend on coordinate or observer, or does it depend?
The cutoff does not depend on the observer. It can be done in curved space. I did the calculations in Minkowski space for simplicity, because this approach to a particle detector had never been used before. So we started with Minkowski space and an inertial detector just for simplicity. But this approach can be used in a curved space. It is actually well used in asymptotically safe quantum gravity.
Okay.
And it has a few more details about how you use it, but it is possible to construct in curved spacetime. But it uses path integrals, which I did not cover in detail in the course. Although they are pretty
Thanks.
much very similar to what happens in flat spacetime. You're welcome.
So you're not really including back reactions, right?
No.
But what tells you that at non-perturbative level, the back reaction won't be strong?
What happens
I
to
mean,
back
this
reaction?
analysis you're doing is a non-perturbative analysis, if I'm not wrong.
Yes, this is a non-perturbative analysis that does not consider the back reaction of the fields. So I'm still considering that the fields are light in comparison with the classical spacetime that lies beneath them. However, I am considering non-perturbatively how the particle detector interacts with the quantum field.
I see. So, but are there any known literature where such effects do back react? Is there something that takes into account the back reaction as well as the interaction of the particle with the detector?
Not that I'm aware of. I do not know of any non-perturbative analysis of back reaction.
No, I'm not asking like non-perturbative analysis. I'm just asking uh, the analysis between the quantum field and the detector while taking into analysis the back reaction also.
Oh, an analysis of the particle detector while taking account back reaction.
Yes.
I don't know much about it.
Okay.
But I would not expect someone to have investigated that.
So what are the, I mean, is there any non-triviality with that?
Sorry?
I mean, I would expect the back reaction generalization to be not that difficult to deal with, at least perturbatively. But do you know of any non-triviality that may arise?
Yeah, what happens is that you have to repeatedly solve the Einstein equation. So you're going to have this to start with, then you can compute what is this guy. And it is difficult to compute this guy already because you have to renormalize this stress energy tensor and you have some ambiguities in how exactly you do this. So you can have some extra curvature terms which make this more difficult. And then assuming you found a way to renormalize this guy, which we nowadays sort of understand how to do, but it is not trivial, then you would have to pick this guy and solve the Einstein equations again, which is now for a more difficult stress energy tensor. So while I know there is literature on this, it is not exactly something trivial. So I don't know whether people who use particle detectors have done this with particle detectors.
I see. You mentioned that we have a good handle on how to deal with the stress tensor. Could you cite that, like which reference you're talking about?
It is a little bit mathematical, but I think every discussion of the stress tensor is somewhat mathematical.
Yes.
My recommendation is the book by Wald. It is, let me see. What exactly is this? Yeah, it is section 4.6. It is called Quantified Theory in Curved Spacetime and Black Hole Thermodynamics.
Thanks.
You're welcome. Any other questions?
I actually have one. When you written the gamma k in terms of the Feynman diagrams, doesn't that make the structure of gamma k a perturbative one?
Oh, that is just an
As you-
illustration.
Oh, okay.
I just did a presentation with the minimum number of equations possible. However, it is important to notice that actually let me go back there. Share screen. Eventually we will get there. Here. This is not necessarily perturbative because of these blobs that let me try to, where is the annotate here? Because of these blobs in here. Oh, they mean that you should consider many other effects, and in here they mean non-perturbatively. So even though this is just an illustration, and actually consider non-perturbative effects, because this means consider all the corrections to the 4-point function up to all orders, for example.
Makes sense. Makes sense.
However, something that is a limitation is that I'm not considering all terms that could appear in the action. So there might appear more terms, more complicated terms than the ones I'm showing here, and I'm throwing them away because that's a way of making the problem treatable. It's what we call truncation, which is this illustration in here. So in principle, you have infinitely many interactions, which are going to follow this curve in the renormalization group evolution. However, to deal with this is in practice impossible. So instead of that, what we consider is just a minor set of couplings. So instead of considering this three-dimensional space of couplings, it's actually infinite dimensional. I consider only a subset of it, such as this two-dimensional space of couplings. And ideally, my truncation, which is this yellow line in here, should be somewhat close to this projection from the exact evolution to the subspace of couplings that I'm considering. So this is an important point. Non-perturbative does not mean exact. Non-perturbative means that you're not assuming the couplings to be small. Does that make sense?
Yeah, it does. It does.
Any other questions? Whether about this class or any of the previous ones.
Maybe I would have one question.
Mhm.
About the renormalization you spoke about. Is it like a UV renormalization? Is it because of UV divergence or infrared divergence, or can it be about both?
The functional renormalization group, it is not exactly about UV divergences, so it is more of how renormalization group is a really weird name because it has to do with renormalization in the UV sense, but it's not exactly the same thing. And it is a very complicated name for the simple idea that in different scales you want to use different theories. So I won't use the same theory to describe a water molecule and to describe the ocean. So I have to zoom out from the molecule to get the behavior of the ocean. And DFRG, it does not consider the UV renormalization. You still get UV divergences, and you have to regularize that somehow else. It does protect you from IR divergences though, because it introduces an infrared cutoff.
Thank you.
You're welcome. Any more
Maybe
questions?
live question, but how different is it from the usual RG that you learn in a QFT course?
It is different because it is non-perturbative. So
Then,
it is
yeah, carry on.
so it is a different method in the sense that it is formulated for you to perform non-perturbative calculations. The usual RG that you learn, the Wilsonian RG, for example, it will typically have a perturbative formulation that restricts you to small couplings. But
And
this
then
one,
there is, yeah, sorry.
yes,
Yeah.
no, go on.
Yeah, so there is something called an exact RG also, right? The one developed by Polchinski and people.
Yes, it
How?
is essentially the same idea.
Okay, so exact RG is what this also doing, but the functional RG is also doing.
Yes, functional normalization group and exact renormalization group are often used interchangeably. And what
I see.
happens is that my formulation is due by Vettori. Vettori, I'm not really sure how to pronounce it, which focus on this gamma K. The formulation of Polchinski, it focus not on gamma K, but rather on WK, which is you have ZK and then you have e to the WK. So it focuses on this different object, which is not an action. So it is more interesting in condensed matter, I think. But in high
But
energy
both
theory,
are non-perturbative formulations, right?
both are non-perturbative.
Okay. So gamma K is, if I recall correctly, it was the 1 pi action, effective action.
Yes, it's
In the
the
usual
1 pi.
QFT.
And this is the connected.
Connected diagrams, yes. Okay, thanks.
You're welcome. Any other questions? Okay, so thank you very much for your interest in this course and for your participation so far. And in case you have any other questions, you can send me an email and I'll gladly answer it. So feel free to contact me if you want. And please check the next courses we will offer on Black Thermodynamics, which will be offered by Bruno De Lucio and Dominic Ryder, and on RQI by Talid Rick Bush. I believe I sent you the email already with some information about these courses, and you can register for them in the same web page you register for this one. So I think that's it, and thank you very much. Let me stop recording.